Hello, testing. Okay. Hi. Good morning or any other time of day. I don't have any good news regarding, I guess a week ago's progress on the causal language model that I was supposed to train. This is a mess, but yesterday I tried like at least 4 times, as far as I remember, to run this. First, it said that I ran out of the free resource that Colab allows. And I said, okay, let's just use whatever is there. Like, I can wait. If it doesn't take 4 hours, let it take 24 hours. I'm fine. And then it just, like, one time it went up to, I think, like, over 70 to, like, 80%. And it still, crashed on me. I guess this is a log. Shutdown. I don't know. I mean, it's not bad news. Yeah, things go wrong. I think one time it said due to inactivity, but I had a YouTube video playing. It was a live stream, I think. And it was just like running. So yeah, I got mad at it. Now I'm currently mad at it. I don't know if I'll be not mad at it. But for now I am. And I'm like disheartened. It does not mean I'll stop learning. It means right now I don't want to talk to it, you know? I don't know if you get that feeling. So right now, this moment, I really don't feel like continuing this, because if our model is not initialized, how do I make it better, you know? Like, yeah. So maybe next time I can run it again and I'm not inactive while I'm running it for like 5 or however long it takes. Yeah, but it's not today. So like, I'm thinking I'm just gonna watch the lecture. Like that's all I can do right now. Presenters that make out like everything go always well make it harder for people to learn. They will be more likely to quit when something doesn't work because it feels it's just them. Okay. Thank you for making me feel better about the mishaps that happen. But yeah, I don't know. Like, I think I wait. I think I could have ran it like past week, but I didn't. So yeah. Oh shoot! What happened? Why did you go to sleep? Huh? Look, my phone went to sleep. Let me wake it up. Why did you go to sleep? That's weird. Okay, don't do that. There. Anyway. Yeah. I'll try again when I feel like it, which is not right now. So I'm gonna play this. We have 16 minutes to go. We're here with problems with reinforcement learning. We are in lecture 12 out of 20 something. This is spring 2024. Let's do this.
Other methods that people are using. Cool. So stabilizing reinforcement learning. So stabilizing reinforcement learning, there's a lot of reasons why it's unstable. The first reason is you're sampling an individual output and calculating based on the individual sampled output, and then there's an infinity of other outputs.
Oh, I haven't checked Discord recently. I should do that. Okay.
Outputs that you could be optimizing over. For MLE, this is not a problem because for MLE, you're always contrasting the gold standard output to all of the other outputs in the space. And you're saying, I want to upweight the gold standard output and downweight all of the other ones. But for reinforcement learning, you only have a single sampled output. That output might be wrong, and that's a source of instability. This is particularly a problem when using bigger output spaces, like all of the words in the vocabulary. Another problem is...
I don't think I got the first problem. Wait. Unstable when using bigger output space, words of a vocabulary.
Instability. This is particularly a problem when using bigger output spaces, like all of the words in the vocabulary. Another problem is anytime you start using negative rewards, because if you start using negative rewards, those rewards will be downweighting the probability of a particular output sequence. And that might be a good idea. Maybe you're getting a toxic output or something like that, and you want to downweight it. But at the same time, in addition to that toxic output, there's like, a combinatorial number of completely nonsense outputs that aren't even English. And so basically you can start to diverge from the natural like language modeling distribution that you have before. So this is a big problem. So a number of strategies can be used to stabilize. The first one is, this is completely obvious right now, and nobody in their right mind would avoid doing this. But the first one is pre-training with MLE. And so you start with a pre-trained model, and then switch over to RL after you've finished pre-training the model. And so this makes a lot of sense if you're training a language model, which I assume that almost everybody in this class is going to be doing. But it does only work in scenarios where you can run MLE. And so it doesn't work if you're...
By MLE, do we mean machine learning? What should the E stand for? I don't know. I'm going to Google that, but... okay. Start with MLE and then switch over to reinforcement learning.
Predicting like latent variables that aren't included in the original space. It also doesn't work in a set...
Oh my god, it's not anything machine learning, it's maximum likelihood estimation. Cool. Okay.
Where like you want to learn a chatbot. You want to learn a chatbot for customer service for a company that has, like, for example, a product catalog that the language model has never seen before. And so if the language model has no information about the product catalog whatsoever, you don't provide it through RAG or something like that, it's going to have to explore infinitely, or not infinitely, but it's going to have to explore too large of a space, and you're never going to converge with.
Predicting the most likely next token, maybe, I don't know. Maximum likelihood estimation. Yeah, estimate. It's just finding the thing that's the closest, right? In something space. Because I see the word space here.
With your language modeling objectives. So you need to basically be able to create at least some supervised training data to train with MLE. But assuming you can do that, I'm assuming that almost everybody is going to do some sort of pre-training with MLE. The next step that people use in reinforcement learning that's really important to stabilize is regularization to an existing model. And you have an existing model and you want to prevent it from getting too far away. And the reason why you want to do this is, like, let's say you start assigning a negative reward to toxic utterances, for example. If your model stops being a language model whatsoever, that's a bad idea. So you want to keep it as a language model, keep it close enough to still being a competent language model while, like removing the toxic utterances. So there's a number of methods that people use to do this. The most prominent ones are KL regularization. So the first most prominent one is KL regularization. And the way this works is basically, in addition, you have two terms. The first term is a term that improves your reward. So you have your old model.
KL, does the K stand for like K nearest? KL. KL. I wrote KL, and it says kilometer. Machine learning. Machine learning. KL stands for, oh, it's a name of a thing? Something divergence? Kullback-Leibler divergence or relative entropy is a metric used to compare two data distributions. No. Yes, you're right. Concept of information theory that contrasts the information contained in two probability distributions. Right. Okay. Cool. Thank you. Yes. Thank you. All right.
Term that improves your reward. So you have your old model, where your old model is creating a probability. It has a probability here. And then you have the probability assigned by your new model. And then you have your reward signal here. And so this is basically improving the log odds, or improving the odds of getting a good reward for high reward sequences. Separately from this, you have this KL regularization term. And this KL regularization term is keeping the scores of, or it's keeping the probability distribution of your new model similar to the probability distribution of your old model. And this beta parameter, basically, you can.
It's discussed in a lot of papers. Apparently really important. I don't think I've heard of it. But I guess it's part of regularization. Let's see if we understand like a little bit.
Increase it or decrease it based on how similar you want to keep the model. Another method that people use is something called proximal policy optimization, or PPO. And this is a method that is based on clipping the outputs. And we define this ratio here. So this ratio is equivalent to this here. So it's basically kind of the amount that you're learning, or the amount that the new model upweights high reward sequences. And so here we have the same thing that we had above. So it looks like this. But over here, we have a clipped version of this.
I think it gets used often to look at training dynamics as how much a model's activation distribution is moving away from a normal distribution. That sort of makes sense. Like, okay, that's interesting. So is that why it's called regularization? Or is that a different thing? Because is that during training?
Where essentially what we do is we clip this ratio.
Where did he go?
This ratio to be within a certain range of the original ratio. And what this is doing is this is essentially forcing the model to not reward large jumps into space. Because if you take the minimum, and actually, I'm sorry, I just realized I might have done something confusing here, because this is actually higher is better. So this isn't really a loss function. This is something you're attempting to maximize. So in contrast to all of the other things that I was talking about before, this is something where higher is better instead of lower is better. But anyway, basically, by taking the minimum of this, you're encouraging the model to keep examining the space where you don't diverge much from the original model. And if the space where the original model was in is better than the new space that your model has moved into, you move back towards the original model. So basically, like if you had, if you learned a model, if you started learning a model that looked like it was optimizing your reward, but then suddenly the model went off the rails and it starts generating completely nonsense outputs that get really bad reward.
Okay.
This will push it back towards the original policy. And that's the basic idea behind PPO.
Keeping it on the line.
In terms of what I see people using, PPO was like really popular for a while, but I started to see people use alternative strategies that use scale regularization. So I don't think either one of them is like particularly more popular than the others. And this one's a little bit simpler conceptually. So I like the top one. Cool. Any questions about this? Okay. And actually, one thing I should mention is all of these things are implemented in whatever libraries you use, like HuggingFace TRL, Transformer Reinforcement Learning is an example library. All of these methods are implemented there. So if you actually want to use these in practice, that's a good place to work. The next thing is adding a baseline.
Now I'm thinking, no wonder someone was saying HuggingFace has a lot of like useful functions during yesterday's looking at other people's code part.
And so the basic idea is that you have expectations about your reward for a particular sentence. And like, let's say we wanted to translate a sentence and we have something like, this is an easy sentence in buffalo, 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 which is a harder sentence to translate. And so we have a reward. If you're not familiar with this example, you can search on Wikipedia for buffalo, 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 and you'll find out what I'm talking about.
I am familiar with it, but I forgot what it's supposed to mean. I don't know what the verb is supposed to mean. Anyway, isn't it longer? How many buffaloes are there?
But there's a reward, and let's say you got a reward of 0.8 for the first one and a reward of 0.3 for the second one. But the problem is if the first one actually,
but I must show you this, or show myself this. Yeah, there we go. See, it's a lot more buffaloes, like I said. And what is it supposed to mean? See, there's a city, an animal, the verb meaning to baffle. To confuse, to outwit. Okay, cool. Animal called Buffalo from the city of Buffalo that some kind of animal of the city. Huh? Bully these animals from that city? Those buffaloes from Buffalo are intimidated by buffaloes from Buffalo. Intimidate buffaloes from Buffalo. Huh. Okay, I like that. I love Wikipedia. So verb 1, 2 verb next to each other. Huh. Anyway.
Is really easy, and the second one is really hard. Getting a reward of 0.8 for the second one for like a translation or something is actually bad, right? And a reward of 0.3 is good because you're moving in the right direction. And so you basically, you have the baseline minus reward, or sorry, reward minus baseline. And this would give you a negative value for this first one and a positive value for the second one. And so the basic idea is, can we predict a priori how?
Being wrong translated as What? Oh, what is that? The 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 curing egg? Is this also an internet lore thing? Someone's written this is lore. If you search Google for translate feature, translated both as, oh my god, how many eggs? Eggplant education. Eggpling? Egg pig? Huh. Okay. Oh. Internet lore is fun.
Positive value for the second one. And so the basic idea is, can we predict a priori how difficult this example is, and then adjust our reward based on that? And so that's the basic idea. You just have kind of like a baseline model. You have a baseline model that predicts this, and you adjust appropriately. There's two major ways you can do this. The first one, the baseline doesn't need to be anything. The only hope is that it decreases the variance in your reward and makes learning more stable. There's two options that I see done pretty widely. The first one is predicting the final reward. Predicting the final reward using a model that doesn't look at all at the answer that you provided. It only looks at the input, or it only looks at the intermediate states of a model or something. And so at the sentence level, you can have one baseline per sentence. You can also do it at each decoder state. And this is basically